Hello everyone, my name is Odarike Charles and today I'm going to show you something amazing. So imagine you are doing a project and you want to visualize this a signal. You have got a signal simulation from LTspice. Now is you find many people will take that value, those values of the array and the value that you have gotten from the simulation, and they take it to another system whereby you can be able to use Python, you can be able to use MATLAB to do that. And you find that it will be like time consuming. Maybe you want to do FFT, the Fourier transform. For that, it's very, very easy because you can do that in LTspice. So today I'm going to show you how you can be able to do Fourier transform in LTspice, fast Fourier transform in LTspice. But first, let's do a simple demo using Python and be able to see what you get in Python. Is it the same thing that you are getting in LTspice? So I'm going to see if they are the same. So I'm going to show you how you can be able to use it in Python and also how you can be able to do it in LTspice. So get into it. So let's start with Python. I'm going to install the following libraries. Import, not to install. I've been using this word, import, as numpy np. Then I'm going to as csp, import sympy as sp, import science, import matplot, lib.pyplot as plt, import, I think that's plt.style.use. I'm going to use sans, then no latex. Yeah, so only that, but you can see these are the formulas that they are always used to do that. All right. From that, I'm going to have two variables, t and f. So I'm going to import a variable from sympy.abc, import t and f. So from that, I'm going to define, let's start with the sign because let's be the sign of t. We know that the Fourier transform of a sign is sine, right? So if you do the Fourier transform of it, you expect to get the same thing. So I'm going to do sol.sp.fourier transform, a Fourier series. Let me get the Fourier series first. Then I'm having y, but you can define the limit from negative pi to pi, or from 0 to 2 pi, because that's the limit you want to do this Fourier series. So I can just leave it the way it is like this. Then I can have the sol.tranget. So I get the same thing. So is it the same? Because when I plot the, let me say when I say plt.plot, let me start with plt.figure. Then I say fig size. Fig size is equals to 10 by 4. Let me use 10 by 4. Then I'm going to say sp.plot. What I'm going to plot just the y, right? You can see this is the y, and if you do the yeah, you can see what am I doing? It's just plt.show. Yeah, so you can see that this is the signal. Both in the frequency, it will be the same because it has only one frequency. So, and we expect the magnitude just be 1, right? So I want to do that simulation in LTspice and see, is it this thing that you are getting here the same way with the Fourier transform. But for the Fourier transform, what we'll do, it will have only a single spike at 1, right? So to get something better, let me have it have a frequency of 1000, right? So if I have a frequency of 1000, then I can be able to go and simulate with a frequency of 1000 on my, so we can see, right? But for those all those that I think it's just SINE, because you can see just the SINE to so you get yeah, so you can be able to see for this 100 having a frequency of 1000, you can be able to see that I think the value at a frequency of 1000, it will be dominant. But at a frequency less than above 1000, you'll find that those values below 1000 and above 1000, they'll be just at a smaller, it will have a smaller value. But at 1k, you'll find that it will be a peak at that point. So let's see if it's true. So for that, I'm going to have this is LTspice. I'm going to have a voltage source, and let me use a resistor as something else. Then I'm going to wire them. Then have a ground there. Have another ground here. Then I'm going to have here 1k resistor. Then from that 1k, I'm going to have a sinusoidal. So I'm going to have a sine. Let me give it a value of 0. It was 1. Then here 1k. Then everything, I leave it the way it is. Then I'm going to, because I need some pulses, let me have like 5. You can see the frequency is 1. So if your frequency is 1k, so for the period is something like period it has uh, a period of 1 millisecond. So I need 5. So if you need 5, it will be 5 milliohm. So I can just type here 5 milli, the stop time 5 milliohm, right? So this is the one. Then I can be able now to run. If I run it, you can be able to see that. But let me do away with this or these plots. I remain with this one, so I can see. I can have add a plot, a plane. Then I can be able to see. So this is the signal, right? Now in this plot, I want to add the Fourier transform of that signal. So the Fourier transform of that signal, I can come to view, then FFT. Then I can choose what to have because I need this V1 here. Or I can, if to make it convenient, I can call it VS, right? V source. So when I do that, I come to this one, view, then I come to FFT, then I can choose that FS or that, okay, I can choose that. Then if I plot it, you can be able to see this is the Fourier transform, right? And this Fourier transform, you can see at 1 kilohertz, we have a peak, right? We have a peak at that value, and I can make it, okay, let me have an active. We can be able to see at that value, at that peak, we are having around negative 6 dB. Around there, yeah. So you can be able to say at 1 kilohertz, we're having majority of the signal, right? So let's see another signal. Let me do that. Let me add different kind of signal. Let me mix or sum different kind of signals. So to sum different kind of signals, I can come up with let me do the simulation here. Let me say from this I'll add sp dot sine of 3t, right? 3 multiplied by t plus sp dot sine of maybe 5 multiplied by t. So let me just have small values. Let me just have 2, 3 like that. So if I do the Fourier transform of this, I'll get just the sine 2t from the, so you'll see that at 2 you'll have a peak, at 3 you have a peak, at 5, but those other values just have smaller values. So let me show you how we can be able to do that. So to do that, I'm going to use a summing amplifier, or I can be able to put them in series. But for convenience, let me have them in a summing amplifier and everything to have just a unit gain. Yeah, to have a unit gain. And I'm going to use an inverting amplifier. So to have a unit gain, you know that we will what? We will short. We'll have just a unity gain. So I'm going to use an universal amplifier. Okay, I can do away with this one. Then I can, okay. So I need a voltage source for V++, voltage source for V++, a voltage source for the for the that, then have our two signals. Let me call this one signal 1, then this one signal 2. Then I can do away with this. Yeah. So from this, I'm going to just then move them a little bit down. Then I'm going to call this V minus there. Then go up. I'll call this one a little bit. Have connect that to that. Then I'm going to have this as P plus. Then I'm going to have a resistor at the output, or I can just have output instead of a resistor. So can be able to see that can call it output. Okay, and this is an output, so you have to choose an output. You have to choose this as an input, this one as an input, like that. Then because I'm using a negative feedback, I need just a gain of 1. I can be able just to have a line that passes like this. There you are using negative, so I'm going to have ground for all of these. Yeah, then for the first two, let me call this one, sorry, let me have it, let me call it V plus. Okay, V plus is here. I call this one V minus. Then I can be connect everything. Then I can have this as, let me call it at S1 to mean that this is signal 1. S1, S1. Then I can have this as S2. Let me connect this to this. And then I need another voltage source for S3. Another voltage for S3. Then I can be able to connect this to this, our ground there, this to this. Then I can be able to delete that, so that I can be able to have that. So I have the 3 signals. The first one is just advanced. Let me have it at a frequency of 2000. So I'm going to have a value 0. Let me have it as a peak of S1, a peak of 1, like amplitude, then 1, 2K. Then I can be able to, I like to have my, let me have it here. Then the second one, the same way, assign. The value here will be 0. Let me have it as 2 because it's signal 2. Let me have it a peak of 2. Then I saw that it was 3K, so I'll have it as 3K and move it somewhere here. Then the last one, because okay, I can rename this one as S2. The last one, it have a peak of what? Let me have as a DC offset of 0, peak 3. I'm just having a different peak so that you can see the signal to have different peaks. So you have a frequency of what? A frequency of 3K. Oh no, it was 5K. A frequency of 5. Let's have a frequency of 5. Let's just say it's a frequency of 5. Then yeah, then I can have these values. Well. Yeah. So for summing amplifier, let me move this a little bit. Yeah. For summing amplifier, what we are going to do here is to, let me name something here. Let me say input, and I'm going to wire it here. Then I can call it an input because it's an input. Yeah. So for summing amplifier, we have to have 3 resistors. So a resistor 1 for this, resistor 2. So I'm going to have a resistor because I need a gain, just a gain of 1, right? I need a gain of 1. and you have seen that the value will be something like 0. I need the feedback to be 0, like yeah, or yeah, a feedback of 0. So I'm going to have 3 resistors and another one here. Then I'm going to wire, because this one are output, then output, output. Yeah, then I'm going to duplicate this one here, one here. So instead of there, I do away with this. Yeah, then I'm going to be having this one here. So I'll wire them. I like to have my work like to be symmetrical, so bear with me. So then I can do away with this other, so that I can be able to see it. Then I'll do away with this one. Then I'll have S3 here. Even there's no need of rotating, because when you wire them, to just, yeah. So from that, now I'm going to have all these values, all these connected to the input. So I'm going to just say input, input. Then I'm going to output, because it's an output to that. So instead of wiring everything, so you can see this. So we have, let's have a value of 1k here. Then also here value of 1k. Also here value of 1k. So I can be able to see that stop time. Let me have it as 1 or something else. So I'm going see the output will just be the summation of these 3 signals. So I'm going to have a value of 15 for the positive, no, a value of negative 15 for the negative, for the to that input amplifier. Then for that amplifier, then I'm going to have a value of 15. So if you run, when you run, you can see the stop time, but you see the I need around this is 5. So it will be like a summation. So I'll take the highest. So this is 5. So to get the stop time, I'm going to have 1 divided by 5k, right? Then I'm going to multiply it by 5. I need 5, so I'm going to have a 1 mega. So I'm going to have here like 1 milli, not 1. It is should be 1 milli. Oh, I think no problem. But it should have a small, yeah, but doesn't complain about that. So I'm going to see, if I hover here, I can see this the input signal, but you don't need that. What we need is the output signal. So you can see the output signal is the summation of these all other signals. So let's assume that you don't know, being given such kind of a plot. Given such kind of a plot, you cannot say that, oh, it has a frequency of this, because you cannot be able to see. So to see what kind the frequencies that are in that signal, you do what you call Fourier transform. So for that, I'm going to show you how you can be able to do that, right? So what you do, you just come to, you right click, then in this plot, then you come to view, then from that view you have FFT. So what you want to do, the FFT is the output voltage, output. So if you do that, okay, so you can see, uh, you can be able to see at this frequency. Let me just hover them, okay. Let's active cursor. So you can see at this plot here is at around 5. Then you come to 3. This is 3. Then you come to 2, right? Yeah. So you can see the value there is 2. Let me adjust this. You can see from this. Yeah, this is the what you are seeing. So you can see that you have a peak at that value. You have another peak at this value here. You have another peak at this value here. So this is how you can be able to see the Fourier series transform of that. So to make it clear, let me make one to be around 50k, 50k, and also run that. So you can see this is the output signal. So this signal you cannot know what the frequency that is in that signal unless you do some Fourier transform. So I can come to this, do FFT, then out. We need to see the output signal. So you can see this is the Fourier transform. And when you place an active cover, you can see that at 50, around 50, yeah, 50, this is 49. So had to have another peak. We come to the other one, it was at 3 and another one at 2. So this is how you can tell the majority of this of the frequency in that signal. So this is how you can be able to do that. And then the last thing I want to show you how you can get the gain or the gain product bandwidth of an amplifier, because an amplifier does not amplify all the input signal. If it has what you call the bandwidth. So I want to show you how you can get that bandwidth. So to get that bandwidth, I'm going to just have an input here instead of or I'm going to have only an input of S1. So I'm going to do this. I'm going to copy this, have it here somewhere here. Then I'm going to, yeah. So I'm going to, instead of having like that, I'm going to have a none because I want to do an AC analysis. So I can have it an amplitude of 1. So from that, I'm going to reconfigure here. Instead of having this transient analysis, I'm going to do what we call AC analysis. So the type of sweep is decade, number of steps is 1,000, then static frequency, let me start at 1. Then because we have 50, I'm going to have end at 1 megahertz, like that. So I'm going to have it like that. So if I come and click here, I can show you something. Let me have it. Let me do away with this plot, right? And let me again do away with this. So it is S1 into this. So it is running at different frequencies. So from 1 to 1000. So you want to see the AC analysis. So we can be able to see it's running. But for that, it's just running the same way. But I want to have at least some gain, because just having a gain of 1, and a gain of 1 has it has maybe, let me say I want to run it until maybe 10,000. Let me run it at yeah, it runs a gain of 1. It runs at every, but I think that this is okay. Let me see. Yeah, it has a gain bandwidth of 10 megahertz, so it can run from 10 megahertz. So let me just increase this to around so that I can visualize what I'm saying. So you can see this plot is decreasing, but let me have a gain, maybe a different gain. Let me have another gain. Let me have it here. Then I'm going to have another one there, and I'm going to have a gain of 10. So let me have a gain of 110 kilohertz and 1 kilohertz. Then I'm going to wire these two to ground, right? So let's see the gain. So we can see the output signal, it has been chopped. If I do not the AC analysis or do the DC analysis, we can see that let me do the DC analysis of it. So I can come to SINE 0, 1, 1 kilohertz. If I run that, then let me see just 5 milli. I can see this is the input signal. Add another plane below. If I come to the output, you see that okay, it's amplifying. No, it shouldn't, because it should showing nonlinearity. Yeah, it should be nonlinear, right? Yeah, I think there's an issue with my configuration. Oh, it was S1. Sorry for that. It's S1 here. Let me repeat. What have I done? Okay, it's just the plot. So I wanted to do the AC analysis on signal 1, not signal 2. That's the issue I was having. So I can just come and have none here, press 1. That is an amplitude of 1. Then I'm going to run an AC analysis on that. AC analysis, so decade, 1,000 values, 1. Let me have just that frequency. Let me add 1,000. So let me have it here. Then no need to. So I can delete this. So if I run that, I can see that to find the output. You can see that's the what I needed. You'll see that it does not amplify um, every signal. It reaches a point whereby this signal that you have into a system, it cannot be done what amplified. So that's how you can be able to run an AC analysis and visualize that the gain bandwidth of your op amp. So thank you for watching. Please subscribe to my YouTube channel. I hope you have learned a lot from this. But the aim was to do Fourier transform and see how we can be able to use LTspice to do that. So thank you. God bless you.